the main goal was to make sure that it's clear in your minds, right? What is the bigger picture? What are the motivations? But also to kind of bring it down to earth, like within this month, right? That's available for the project. What can you accomplish? So it's good to be very concrete on what you can promise that you can deliver, right? But at the same time, keep in mind the bigger picture. And of course, the hope is if you're successful in getting the project to a good shape, you can take it further, submit it to any research venue. So that's the idea. Any questions there? And I think we added on Piazza an announcement, right, Gwanya? Did we already send about the deadline next week to send the revised? Yeah.
Sometime next week.
Yeah. So just a week, sometime you can. So send us a revised proposal. Now, based on what we've talked, try to make it now more detailed. Add pointers on what you will deliver, what you will have at the end of the project. And of course, when you present the project outcome and the report, right, we will compare on how that aligns. And the idea is this is also important, right, to be able to plan and to be able to say what you expect will turn out. Of course, there will sometimes be surprises, and it's good to have some kind of surprises, right? The good ones, especially if you do more than what you promise, that's a good thing. So I won't hold you up to that document to say, right? But it's just mostly a way for you to help plan better. So that's the goal. Yeah. So I want all the teams to submit a revised one. Any questions there? Because I think, when I had some of the discussions, right, it was still vague in terms of what you really want to do. I mean, some of you picked projects that were already kind of suggested, right, which is good. I mean, there's something concrete, but in that case, you may not have understood the full implications of it, or why do this, right? Why this particular method, or why pursue this? It's important to have that be clear in your mind. And in that case, talk to the mentors who presented those ideas and make sure you're on the same page. Right? In other cases, I know people were trying to tackle an entire area in a project proposal. That's great. You want to read and explore that, but that can't be a project proposal, right? And I think we explicitly told that when we wrote guidelines for what's a project. So you cannot say, I will do X, right, which is a book. That cannot be a project proposal. It has to be more concrete than that. But I think in most cases there was definitely, a lot of good thinking and good ideas. I think almost I can imagine all of them, right? Not almost all of them have potential to be published at some research venue. I truly believe that. So I hope you can. I want to make sure we are able to guide you to do that well. And that's beyond the class project, so that's not, again, a requirement, but I'm sure you'll be motivated to do that. So you can continue those discussions even after the course. And that was also the goal, to have that as a workshop, right? Gwanya, what is the date? I forget. We already set the date March. Right in the beginning, and we already made that announcement, right? It's March. There in the course outline. So if you can't make it, let us know early on. I hope you can, because again, the idea is we'll have this as a mini workshop. We'll also open it up to others. So we'll have, we'll have open doors. Anybody can attend your talks, get to know of your work. So I want that good interaction at the end of the course. Any questions on the projects? All good? Great. So now let's get back to the course. And graphical models. I know this was a slight change in the outline I published because we didn't have graphical models in the outline, right? We had optimization, and so we will kind of, but we had some, I think, spare lectures in the end. So I'll continue to do graphical models today because I realized that probably there is no other course on campus where you will get these kind of ideas, unless I'm mistaken. I don't know if people have done other courses. I don't think that's the case. So I want to make sure we cover some more of that. By the way, I'm curious how many of you had done a course on graphical models or used it, seen it before? Okay, so this is useful, right? So always feel free to give me feedback if I want to make sure that I'm aligned to what, your background, and if you've already done things, we can easily skip over. But it seems like so far, right, most of the things I covered, I think the majority of the class, hadn't seen it before. Is that an accurate statement? Great. So the last class, we were looking at graphical models. Right, we introduced the notion of a Markov graph, and the idea was this models conditional independence relationships. Right, so we had this graph, right, that's made up of nodes and edges. The nodes were the variables. The edges were giving us conditional independence relationship. Right, so in the most general form, we said there is this global Markov property, which is notion of separation on the graph, right? So if you have separation on the graph, that implies conditional independence. And so this general separation principle, right, is you have sets A, B, and C, and if C separates A and B on the graph, you have conditional independence on those variables, right? You condition on C, you separate A and B. And so you can think of conditioning as erasing those nodes, right? So if you don't have any more connections, that means there's conditional independence. Right, so this was the basic notion, and towards the end we also related this to tensor diagrams and tensor networks, which I think is really cool because there's a rich community working on tensor networks, and there is a really close connection, right? And the main idea was, if you're looking at tensor networks, there the nodes are tensors, right? And the edges are contractions. So if I have like just outgoing edges without any connection, that means it's the order, right? That's the resulting order of the tensor. In this case, it's order 2, which means it's a matrix. If I had 3 edges going out, that's an order 3 tensor, right? But the interesting thing is now if I join 2 different nodes, right, in this case, there's a contraction along that index, right? Meaning I can sum up over that index to get my resulting output tensor. And the nice thing was this duality principle we showed in the previous class, right? And the duality principle is the Markov graph is dual, right, to the tensor network. What we mean by that is, if I tell you there is a graphical model with a certain graph, and then I form its dual graph, right, I can do contraction on that tensor. And contraction there relates to marginalization, right, in the original graphical model. And I think this is right. I mean, you don't have to use this transformation, right? You could just stay in the graphical model realm and reason about marginalization directly. But then there are many tools that are available for tensor contraction directly, right? So this kind of gives a bridge to connect the two programming frameworks or communities, right? So it's not fundamental in the sense you don't have to do this transformation. It's just a nice property. Right, and that was the idea that, to give you one example, we did this chain graph, right, or Markov chain. So you have the Markov chain as a graphical model, right? So here, the node J was conditionally, made the two parts conditionally independent, right? And now if I take the dual graph of this, right, so it was, the edges are now nodes, right? So ij and jk are now the nodes, and then you have this hanging, right, on this. And what this says is now if I do contraction, right, along various nodes, right, various edges, I take that back, right? So in tensor diagram, you always contract along the edges. You contract along that edge, you can marginalize out that particular variable in the original graphical model, right? So in this case, if I marginalize I, that means I just kind of contract along that edge, right? I marginalize along j, I contract along this edge. Right, so I do the relevant contractions to get my marginal distributions. So if you're looking at marginalization, this tensor network is much more convenient, right? Because it directly tells you along what edges you want to contract. Any questions here? Right, and it need not be along a single edge, right? In the end, let's take another example. If I have a model like this, what would be the dual graph now? So I have, I guess now, the nodes are ij, right? I have ik, I have il, right? So, and then you have this, right? L, J, I. Oh, sorry, L, J, K, right? Do you agree? No, sorry, I should not, I should have ij. No, this is wrong, right? What should it be? Okay.
Yeah, because everything is aligned, so for sure there is also
should be a triangle, right? Exactly. Okay, good. Ik, il, and then there are things hanging out of that. Okay? Okay, good. Good, we're paying attention. Okay, so now if I want to marginalize, it's very clear, right? If I want to marginalize I have to do kind of contraction along all these edges. If I have to marginalize the other nodes, those are leaves, I just kind of contract along that one edge. Okay? And the contraction in this tensor network, people also call it Einstein summation, or in Python it's einsum. So again, just another name for the same thing. If you come across this, it's all kind of related to the same one. Any questions here? Good. So we were talking about marginalization. Of course, the question is, can these graphs give us more tractability in marginalization, right? If you recall in the previous class, we did the Hammersley-Clifford theorem, sorry about my spelling. Right, the Hammersley-Clifford theorem said, if I have positivity, right, there was this condition that no configuration is ruled out, right? You have non-zero probability on all the configurations among all the nodes. Under that condition, we said that the probability of the joint distribution can be written in terms of this Gibbs form. And in the most general case, that was in terms of cliques on the graph. Right, and we said this is great, it's factorized form, but the problem is the normalization, right? So this normalization would mean I would have to sum up over this all possible configurations, right? And in general, this is, if even each variable is binary, right, implies that all possible configurations is 2 to the n, right? So it's exponential. So just the aspect of marginalization is non-trivial, right? So this is, right, I mean, normalization is, I kind of sum up over everything. If I want only over some subset, I can sum up only on that subset of variables, right? I marginalize out those. And all of these are hard. Right, so for general graph, this is hard, right? And then we said when it's acyclic, we have a much cleaner form. And in this case, the joint distribution, you can directly relate it to the marginals, which is great. And marginals only along the edges, right? That's all, those are sufficient statistics. We have this form. Right, so this is now kind of, both are factorizations, but this is a factorization where we can directly connect it to the marginal distributions. And that was a huge, difference between a general graphical model and acyclic graphical models. And now we'll briefly see, if you want to do marginalization in an acyclic graph, right, it becomes much more tractable because of this form compared to a general graphical model. And for this, we'll just, I'll just demonstrate this on a chain graph, right, because, it's just much quicker to do this. So let's say I have 1 through n nodes in my chain, and I can write down my joint distribution, right, just in terms of, let's say P of yn, P of yn minus 1 given yn, so on, right? So I can just write it in terms of the distribution at n, and then I can go backwards. Or I also have the equivalent form where I start from the first node and kind of go forward, right? This is kind of the forward and backward interpretation, right? I can write down my joint distribution starting from any of the leaf. Right? And that's true in a general tree as well. I can start from any leaf, and I can I can start from any node and conditional on it. So in the chain, it's just the end, right? So I can go back and forth. And the main idea is if I now want to say compute marginalization, right? So let's say I want to compute this over all yn except, I such that I is not equal to I star. So I'm giving you the joint distribution. Can I compute the marginal from the joint distribution, right? So that's the goal. And now if I have it on a chain, right, I can do this in an iterative form, right? I mean, of course, if I had to do it brute force, this would be, let's say, even if they're binary variables, this would be 2 to the n minus 1 configurations, right? So I don't want to do this brute force. But the question is this form going to help me further simplify the equations? And so for this, we can kind of do the divide and conquer, right? So the main thing to remember is that the dependence on the variable yn is only in these two terms, right? So I can kind of like evaluate just that and keep that sub-problem and do that kind of it and propagate that iteratively, right? So the message, and because we'll kind of extend it to general message passing algorithms, the message would be, right, the message going from n to n minus 1 node, right? And that would be in terms of, right, so I'm gonna use the form where the joint distribution is only in terms of this potential form, right? So I mean, of course, if I had the joint distribution directly like this, right, I would be done. There's nothing to evaluate. So I will just make sure the notation is consistent. Right, so I want to start with this form and go to the marginals. Right, that's the form I'm given, right? So there's no learning here. Right, that's why this is called inference, right? Because I've told you all the parameters of my joint distribution, right? There's nothing to learn here. I just need to marginalize, right? That's the problem. Okay? Are we good? Yeah? Sorry, yi and yj, yeah, comma, in general. Yeah, in my mind, that's what I meant. Right, so all I'm saying is we know that if it's an acyclic graph, right, chain is a special case, the joint should be related to the marginals in this form, right? But I could give you a different form, right? I could give you in terms of potentials, and I ask you to relate that to the marginals. Right, so, and I cannot directly just match this, right, because there's many transformations you can make so that the joint is still the same. Is that clear? So I want to go from this form, right, to this form. Good, so I'll now describe my messages in terms of just marginalizing this partial answer, right? So we know it is in this form. So instead of this, I'll write everything in terms of potentials, right? So I'm going to write it in terms of sigma n of yn, right? Then there is sigma of n comma n minus 1. This is the edge, right? Yn and yn minus 1, so on, right? So I can just expand the, of course, this product, right? So all I'm doing is I'm expanding this from the last node to the first node. And the idea is the variable yn appears only in this two terms, right? It's not in any of the other terms, right? Because that's kind of corresponding to the node and the edge potential. Yeah? So I can just do that partial summation. Right, so this is my message at, of course, this is a function of yn minus 1, right? And will kind of write it this way because this is the message I'm sending from node n to node n minus 1. Right? So the message is this partial answer, right? There is the overall marginalization I need to do. I can start with the last node and just pass the message in this direction. And now at node n minus 1, again, I can kind of take this, right, and kind of propagate it forward, right? So I'll just write one more just to kind of, so from n minus 1 to n minus 2, the message I will send will be a function of the value at n minus 2, right? And what I'll do is I'll use the message that was sent to my node and also combine it with the potential at that node and edge, right? So I have like, right, the message here, which is n comma n minus 1 of n minus 1, right? And then I have the node potential at that point, and then I also have the edge potential of the next edge, right, from n minus 1 to n minus 2. And now I marginalize this over n minus 1. Right, I mean, this is simply just divide and conquer, right? Instead of doing the summation in brute force, I'm just doing it one by one. And the chain structure allows me to decompose this completely. Right? And now I can, kind of go on until, right, I hit this node, and then I can also have messages be sent from the other direction. Let's say this was my I star where I needed the marginalization. I can kind of compute all the way here, right? And then that combine the two, and then I get the marginalization at that node. Right, and I get the answer exactly.
So I'm just wondering, so from a graph perspective, are you just starting from like source nodes and going in? Like,
I mean, there's no direction in the graph, right? But you can, and in the general case, you don't, you can start at any node, right? But in this example, it's just becomes convenient to start at the leaves and go inwards, right? So on a tree, the more generally, you can just kind of start at all the leaves and just kind of, you can arbitrarily root the tree at any node, right? And in this case, you want marginalization at a particular node, that's the root, right? And then you kind of direct that towards the root.
And this is just for acyclic, right?
Yeah, I mean, even just for chain, right, at the moment, I mean, I've only demonstrated it on chain, but you can do that for any acyclic graph. And that's when it's exact, right? So all I've done is divide and conquer, right, because of the factorization form. Okay, so there are many improvements you can do here, right? So in this case, we were just computing the marginal at a very specific node, right? All the nodes knew that before, and they were passing the message this way. But you can also extend this to computing marginals at all the nodes, right? Because if you have the sub-answer here, it could be reused to computing the marginal at another node, right? Other than, of course, so you can kind of reuse the same answer to compute marginals at all the nodes. So in that case, you just kind of pass messages in both the directions, right? So every node has messages coming from both the directions on the chain, and hence you can compute all the marginals. So that's a kind of a simple extension from just doing it at a single node. Because anyway, you reuse the same messages to compute marginals at any node, right? I can reuse the same. So okay, this is great. So if I have a general graph, what would fail? Or would this work? Of course, the challenge is the cycle, right? So here in this case, you had a particular node, you could just kind of in this special case of marginalization of a single node, I could just route all my messages to that and then I'm done, right? On the other hand, if there is a cycle, how do you direct it? You cannot, right? So cycles means there is inconsistency, right? You cannot just break down your problem. Right, because now the terms here are just not what we wrote down, right? You cannot break it down into parts because having the loop means you violate that. And so that's why for general graph, this is hard, right? I mean, computing the partition function, this normalization factor is called partition function, by the way, is sharply hard for that reason, right? So you don't get tractability for any arbitrary graph. But you can still use it as a heuristic, and that's what people do when they do belief propagation algorithm. So belief propagation or message passing means you do exactly, this form of messages for any pairs of neighbors, right? So in a general graph, right? So now I have a general graph. Now I'm going to pass messages between two nodes. I want to make sure I use the same notation as here. Yeah. Right. So again, we have the general graph with potentials, right? So let's assume that I have this. Right, so from this, if I want to get the marginals, so this is the message going from node I to node J, right? And this message involves, right, marginalization. So essentially it's the same, right? So if you recall earlier what was the form here, you had the message coming from the other nodes, right, other neighbor of this node n-1, and you combined it with the potential along that node and sent it outwards, right? So the way can you see if I write here? No? Okay, I'll write here. So the idea is, right, now I'm sending the message to node J from node I. What I will do is I'll look at all the messages that were sent from all the other neighbors to I, right, other than J. I'll gather all those messages, right? In this case, that was just this, right? That was just the one message. And then I'll gather the potential along these two nodes, right, and the node potential, sum it up and send it along that node. So what I'm doing is just directly extending what we wrote for the chain and for a general acyclic graph to even when there are cycles, right? So we're just writing it down, but we can then debate whether that's a good idea or not. So the idea is I'll look at all other nodes k other than j, right? So k which are neighbors of I but not j. So I'm going to look at all those messages. I'm going to sum up over all those messages, right, of the variable I, right? This is the dummy variable. And I'm going to add in the potential between I and j. And then the node potential as well. This is just exactly this equation, right, for a general graph, right? So instead of here in this case there was just one edge here and then another edge, right? You could have many edges in the general graph. And I can do this at all the nodes, right? So in each iteration, each node can send out messages as well as receive messages, right? And you can update again, do the same, right? So this is called like iterative belief propagation because you keep doing this again and again. Whereas in the chain, we always said was you need to just do once, right? And you're done. But we know in the general graph there are cycles, right? So you can't do once, right? That's not defined. There's no consistency, right? The messages will differ. They don't align because you get messages from different parts of the graph. But hopefully, if you do this many times, it can converge to something meaningful, right? That's the hope. And there's been an extensive line of work showing in many cases it does converge to good answers. In fact, it can converge to correct answers in many models, even when there are loops, which is surprising. I think one result that is nice and popular is in the Gaussian belief propagation. So if you have Gaussian random variables, right, belief propagation is nothing but right, converting potentials, which is the inverse of the covariance matrix, to covariances. Right, so what I really need is a way to kind of compute my means and covariances from these potentials. And it turns out that the Gaussian belief propagation can converge to the correct means if the model has some nice properties. And one special case is when it's attractive model. So attractive model means all the correlations are just positive, right? So you don't have any negatively correlated variables. So in that case, even the loopy belief propagation converges. So people also add loopy belief propagation to emphasize this is done on a loopy graph, right? So there are some special cases where you can prove that this works. In most cases, you cannot prove anything, but in practice, it seems to yield many reasonable results. Right, and there's also the intuition of this working well that's connected to the phase transitions. If you recall in the last class, I kind of had a brief discussion on right, how phase transitions relates to the strength of correlations in the model. Right, the gaseous state is where there are no long-range correlations. Right, in that phase, we also see that loopy belief propagation converges to good answers. And in fact, there's theory in many settings where you can prove that it converges to the right answers. Right, so those are kind of the easy cases where these simple greedy updates can converge to good answers. Is that clear? Right, it's message passing, that name is clear, right? Because you're passing messages along the graph. Right, so for each node, along each edge rather, you pass the message, but like look at all the messages accumulated from the other neighbors. Right, so of course, as I passes to J, J will also be passing to I, right, in the other direction. So you are collecting messages all across the graph. And message passing is more general than just belief propagation, right? So here we were doing this for a specific case of marginalization of the distribution. You can use message passing in so many other settings. For instance, Zongi is looking at graph neural networks, right? So there again, you can update learning of the graph kernel by passing messages, right? I mean, which is very, essentially the same form, right, you're going after as in this graphical model. So it's essentially a graphical model where you're learning the kernel. So that's the kind of some general comments, right? So loopy belief propagation in general is wrong, but there are lots of practical scenarios where that can give you good answers. And since it's the cheapest thing to do, people anyway start trying that, and if it fails, go to more sophisticated methods. And by the way, that's not just for marginalization. I can also do what's known as max marginalization, right, or max marginals. So which is, instead of summation, I can like look at maximization, right? What is the most likely value configuration of my distribution or part of my distribution, right? So I can do even a combination of max and sum. And all you need to do is replace the max and sum here, right? So the same notion of propagation along the graph holds. So you can also do this for finding map estimates. Right, so if I want to find the maximum configuration instead of marginalizing, I can do that. Right, that's direct. Any questions here? Yeah, so this was about looking at belief propagation and using that for marginalization and maximization. And just to go back to the tensor diagram comment we made earlier, you can also essentially, like, the belief propagation is passing messages along the graph, right? You can view that as contracting certain edges, right? So you can also view that as tensor contractions that's equivalent. Right, I can either pass my messages along edges of the graph, or I can contract my tensors where the nodes are those edges, right? So it's just an equivalent way to express the same algorithm. Okay, so do you connect like kind of this message passing to also contracting the tensor? Good, so given this, we'll now look at learning the structure of graphical models, right? Because so far there's been no learning, right? I mean, hopefully you've learned about graphical models, but we haven't dealt with the problem of learning in graphical models. So, because there we assume that the joint distribution is given, just that it's given in the terms of potentials, I wanted to convert it into marginals, right? That's the problem we looked at so far, and we termed that as inference rather than as learning. Okay, so this problem we looked at is inference, right? But we want to now do learning. Great, so if you want to learn a graphical model, you want to learn both the graph and then the parameters, right? But the very first thing to do is learn the graph, because if I don't know the graph, I don't get simplification of my distribution, right? So I don't know how to fit parameters too, because I don't know what are the non-zero edges, right? So you want to only have functions along the cleaves of the graph. So the first stage is always graph estimation, right? So we call that structure or graph estimation. And sometimes it's also called discovery problem. Especially in causal inference, they call it discovery, which is the same as structure estimation. Now it's called discovery because I'm discovering what the relationship is, right? And the other part of learning is just then you can fit parameters. So that's what we try to distinguish the two. So of course, as you can imagine, for general problem, this is also hard, right? I mean, every aspect is hard. So we'll, as usual, first limit to trees and ask, can I learn a tree graphical model, right? And in fact, you can take it further to say, I want to approximate my distribution as a tree graphical model, right? I could have some arbitrary data distribution giving me samples, right? I'm willing to do model approximation. I don't need to learn the exact distribution, right? Anyway, you can, all models are wrong, right? You're always trying to summarize your data into a compact model. And so natural first step is to ask, can I fit that to a tree model? Right? And the benefit of fitting it to the tree model is then I can do all these inference through belief propagation, right? And we know that part is exact. So if the tree is not a bad approximation for the data, it's okay, right? So that's the justification. Of course, we can further enrich it later, but let's start with that, right? So the idea is, let's say I have a whole bunch of samples drawn IID from some distribution, right? This is any arbitrary distribution, right? I don't care what that underlying distribution is. But I want to find the most likely tree distribution that fits this data. Right, so I'm doing maximum likelihood estimate as before, right? We did that in the first part of the class. And what I want to do is I want to maximize over distributions Q such that Q is a tree graphical model. Right, and I want to look at what is the likelihood that Q assigns to each data point. And of course, I want to look at the sum of the log likelihoods, right? This is IID data. Right, so all I've written is just the formulation for the joint distribution, for the maximum likelihood. So far, I have not used the fact that it's a tree. So just a general comment, again, this is true for any maximum likelihood, right? This is equivalent to Kalbeck-Leibler distance minimization. I may have briefly pointed out during the statistics part of the course, but I just want to emphasize that, right? So this is true for any maximum likelihood, we are not using the tree. And that relationship is you can always look at maximum likelihood estimation as minimization of a certain Kalbeck-Leibler divergence. So where I use the empirical distribution of my samples and then minimize over Q, over whichever class I want to. These two are equivalent problems. So P hat is the empirical distribution. So we'll limit to discrete again just for the sake of argument, right? You can also think about empirical estimators for continuous distribution. You can have like a kernel density, for instance. But again, just for simplicity, let's assume the samples are discrete, okay? This is not a limitation, just a simplification. First of all, do you see this? How many of you, or do you recall the definition of Kalbeck-Leibler? Yeah.
Oh, I forgot which one is P or Q.
Yeah, the first term is always the one that comes first. So it's expectation of P log
Q over P.
P over Q, right?
P over Q.
Yes. Of course, expectation means I'm like looking at the, right? So I can rewrite this as in terms of the negative entropy, right? So this, I'll just do it, this is true for any distribution, right? So this is now just a fact, right? So all I did was expand this log P over Q, right? This is by definition, this is the entropy. So I hope you've seen that, right? So if you've done information theory, you will realize this is entropy, right? So all I've written just is the formula, right? So, but now you can see the equivalence, right? If I want to do minimization of Kalbeck-Leibler divergence, that's equivalent to maximizing this term, right? Because I can now look at Kalbeck-Leibler between my empirical distribution, right? So I'm just kind of trying to relate this term, right? So this first term has nothing to do with Q, right? So if I'm minimizing over Q, I can drop the first term, right? The answer is still the same. And so that's equivalent to maximizing the second term. So what does the second term look like? What is expectation over the empirical distribution? That's exactly this, right? If I'm now looking at all the realizations of X, that's nothing but expectations with respect to the empirical distribution. So this is just a compact way to say it's maximum likelihood, right? But I think it's also a nice intuition, because if you're doing maximum likelihood with respect to Kullback divergence metric, you're looking at what is closest to your empirical distribution, right? So this is where, if you do information geometry, right, there is the book by Amari, which Gaussian is looking at, where you can think of this as an information divergence projection, right? So let's say this is the manifold of all distributions Q in the class, right? In our case, it'll be the class of all tree structure distributions. And I have some empirical distribution here. The empirical distribution, in general, you don't expect it to be a tree, right? If it's exactly a tree distribution, I'm done, right? There is nothing more to estimate. But because it's not a tree, I want to look at what is the closest distribution to this empirical one that's a tree, right? And this is called information projection, right? I'm projecting with respect to Kullback-Leibler divergence. Okay, so it's an interpretation of maximum likelihood, but I think it's a good interpretation to think about, because now you can view it as projections, right? The only catch is this Kullback-Leibler distance is not a metric. So you can't kind of use all the nice projection theory, manifold theory directly. You have to work more, right? That's why kind of technically it'll be more involved than kind of directly thinking in terms of manifold theory, but many results do carry over. And I think for now, we'll just use it as a nice interpretation. So I won't go into any more details on information projections. That's a course in itself. But just keep in mind, when you're doing maximum likelihood estimation, you can view it as an information projection. Right? I'm projecting my empirical distribution onto this class of distributions that I'm constraining, right? And in this case, I'm constraining them to be tree. Okay, so this is true in general, right? So this is nothing specific to do with tree distributions, but I thought it's a good notion to have. Any questions here? Is this clear? Good. Okay, so far it's very general, right? The question is, what can I now do that uses the fact it's a tree? So that's where we'll actually use this identity, right? That the joint distribution can be factorized. Of course, now I'm using the notation Q, so I will just like kind of do this with Q. It's true for any case. And so all I want to do is maximize this expected, right, log of Q under P hat, right? So I can, if this, just in terms of identity, it's with respect to distribution P hat, right? Just notationally, because I shouldn't multiply again. When I do the expectation, I'm already multiplying P hat. Let's say xi. So x is the dummy variable here. I mean, when I say expectation, I already multiply with P hat of x. So I was just, my notation was off. I guess it was off here as well, right? So the expectation is with respect to P hat. If I'm directly summing over, I'll write it as p hat. So this is nothing but p hat of x log p hat by q over x. Okay, so I just mixed up the two. When I write expectation, I shouldn't be multiplying with the probability. Is that clear? Okay, so all I need to do is maximize this quantity, right? So maximum likelihood is the same as saying maximize now p hat is my empirical distribution. So note that when I write summation over x here, it's over all possible configurations, right? So we looked at discrete distribution. It's just all the values this discrete distribution takes, right? Over all the n variables. That's what this is, right? Because p hat is the empirical distribution, right, among all my nodes in the graphical model. Okay? Because what I'm getting is in each sample is a vector, right? I'm getting values at each node. Yeah? Any questions here? Do you understand the problem? The problem is, right, I have like values at various nodes, right? 1 through, let's say, maybe I'll make this capital N for the number of samples. So I have n nodes in my graph. I just don't know what the edges are, right? So I want to approximate tree distribution. So I want to find what is the best tree along these nodes. And I get many samples from all these nodes. So each sample has length n, right? Because it's values at all the nodes. Okay, and the empirical distribution is the joint empirical along all the nodes, right? That's what I have. Is that clear? Are we good? So that was the joint empirical, right? And now when I sum over here, I want to write down all possible configurations over my joint distributions. Okay, so I won't be actually evaluating it, right? This is hard. If I directly try to do this, again, if each variable is binary, this is 2 to the n configurations, right? So I shouldn't be doing this with brute force. But the hope is I can utilize this factorization form and simplify it further. And in fact, we can, right? Because, I mean, this p hat of x is fixed, right? I'm not optimizing on that. I'm only optimizing on q. And then q, I can just plug in this distributional form, right? I can directly use this form. So what I can do is I can, and in fact, I will just separate the two parts, right? So let's say q of xi, that is just the marginal at node I, right? So, and when I sum over all the x here, right? So what happens is you can marginalize at all the nodes, and there's also sum over I, right? I can just exchange the two parts. Okay, because the log, the products become sum. So just the first term, right? I'm just taking the first term, plugging that here. And similarly, I can do for the second term. Okay, so far so good. Right, I can just plug in this. There's also these terms here. Sorry, x. Yeah, we can keep everything as x. Right, all I did was substitute this here, right? That's what I've done. And the thing is, there's some very nice properties you can have, right? Because here, now the only thing that matters is node I, right? Like I put the summation outside. So I can marginalize over the rest of the distribution except at I, right? So this is now nothing but I can just safely marginalize everything else except node I, right? So I can, instead of this joint distribution, I can just say, I want to look at the value just at I, right? And intuitively what you want to do is match the marginal distributions, right? That's when you would have the best answer. So if you want to maximize this quantity, you want to match the node marginals and the edge marginals. So again, this is a claim, right? You can check that quickly. The claim is if you set at each node, right, the node marginal is equal to just the empirical marginal distribution, and again the edge marginal is equal to this. Then you have the maximization. And here I'm fixing the graph, right? So there's also maximization of what the edge configuration should be, right? That's still outside here. So this is max over edge such that it's a tree, right? I still have that outside. But for any fixed graph, I can just set it to the node marginal and edge marginal, right? So claim is for any tree, right? I can set this to be right. So what I'm doing is searching over all possible trees, right? So think brute force. I can just take a tree, right, and look at what is the best distribution if I fix this tree. It turns out that the way to do is just match the node and edge marginals. And that's kind of intuitive, right? Any mismatch would even make it worse because of the form of this distribution. So if I match it, I get the best answer. And so if that's the case, then now all that's left is maximizing over all possible trees, right? So the inner maximization, I can already take care of it. So outside there is still, right, over all the trees I want to look at which is the best one. But here I can substitute my marginal distribution of Q in terms of just the empirical distribution. So the first term is nothing but the negative of entropy of the empirical distribution, right? That is nothing to do with getting the best tree, right? It has no dependence on the tree structure, right? This first term has no dependence on the tree, right? So I can leave that out. The second one, now I'm going to substitute here, right, this edge distribution with just my empirical distribution. Do you see? All I just did was write the substitution. I dropped the first term because that has nothing to do with maximization of the tree structure. Any questions here?
But it seems we're still only capturing the correlation, not the causation of the tree.
Oh, we are not talking about causation, right? So there's not causal I mean, it could be depending on if you have intervention and other data. So recall, we are only doing undirected graphical model. And if I don't have interventions in general, right, I cannot specify. So on the tree, I can always root the any node and direct all the edges there, right? So without further information, they're all equivalent good models. So we can't say which one is the cause and which one is the effect. So these are undirected. So are people comfortable with the math here? What do you recognize that quantity to be? This term? What is it? Just had the expression on the other side. What is it? So KL between what and what?
Between the empirical distribution. Oh, yeah. So it's the empirical distribution for variables.
So by the way, this marginalization, right? I can easily marginalize all the other variables except the ones that relate to INJ, right? Because the rest of it don't matter. I can just take away that distribution and I can just. So now it's just the distribution along the edge, right? Of course, it's the KL divergence between the joint and the product of the marginals. If you, in information theory, what do we call this? What is this quantity equal to if the distribution is independent? It's mutual information, right? And it's zero if they are the independent distribution, right? Because the numerator and denominator are the same. So this quantity is called mutual information. And so what we are doing here is maximizing the empirical mutual information, right? I'll just use this notation to denote this inner term. And we are asking, right, what is the maximum sum of mutual information along the tree? Can I find this efficiently? What does this problem look like? I'm asking you to maximize a certain sum of quantities along edges of a tree. What is this problem? Going back to algorithms course, what is this problem? One of the first problems you probably look at. Do you understand the problem? My worry is you probably don't understand what the problem is. You're maximizing, right, the sum of certain weights along the edges of a tree. You want to find the best tree, right, that maximizes the sum. What if I had minimization instead of maximization? Exactly, right? So this is the minimum spanning tree problem, right? There's all the Kruskal's algorithm, there's all these variants that you can do this efficiently, right? This is polynomial time. Okay, so on the tree it becomes tractable, right? So if I want to ask what is the best information projection along the distribution that are tree structured, right, or factorized along the tree, I can do this for any distribution. Or in other words, I can find the most likely tree distribution efficiently. It's called the Chow-Liu algorithm, dates back to the 60s, right? So it's kind of nicely combines like notions, right, of computing the best spanning tree, but also notion of mutual information maximization, right? So, and it's also very intuitive, right? You want to maximize mutual information along the edges. Like, if you now have like a chain like this, there's stronger mutual information here than between the non-neighbors. In fact, this is called data processing inequality in information theory, right? So data processing inequality means the mutual information between non-neighbors is less than between neighbors, right? And you can see that that's why maximizing the mutual information makes sense. I mean, if I had the exact mutual information, I can just compute it, but when I have samples, all I can do is compute my empirical mutual information, right? So I estimate what I believe is the true mutual information, and then I look at what is the best tree that maximizes that. Okay, so it's very intuitive, right? Because, when I don't have loops, I know the mutual information decays along any path. Right? You cannot have strong mutual information between nodes that are not neighbors. And so that helps us figure out who are neighbors very easily.
So I'm just wondering if this gives you like continuous values, do you threshold to like eliminate some edges? Because otherwise, if the graph is like fully connected, then you're not going to get efficiency gains.
I mean, that's why you limit it to being a tree.
Oh, right.
And that's why in the general graph, none of this is true. Right? So in general graph, you wouldn't just have a chain, you would also have some loop here, right? So you cannot guarantee that the mutual information between non-neighbors will be smaller. You could have all kinds of like buildup of mutual information, and you could end up with strange configurations. So that's why all this kind of doesn't hold when you have loops in the graph. Loops are bad when it comes to graphical models. Any questions here? Good. So, so in the remaining time, I can quickly say what else we have right in the space. As I said, when there are loops, you don't have guarantees, but you could come up with some form of local testing for finding the structure. If you recall, we had the local Markov property, right? So there the idea was if you could if you had neighbors, you would be able to conditionally be independent on the rest of the graph. So you can turn that into an algorithm, but of course in this case, we have the complexity growing exponentially in the degree of the graph, right? So this is a simple trick, right? So if you recall, the idea was when I had the node, I conditioned on the neighbors of my node, right? I would be conditionally independent from the rest of the graph, right? This was my property, the local Markov property that, so this was conditionally dependent from all other nodes when I condition on neighbors, right? When J is not the neighbors. So I can just kind of use witnesses, right? So let's say my degree is bounded, right? So let's say at all nodes my degree is D, right? So at each node I can just combinatorially select all sets of size D, right? And I can search over this, I can do the test, I can find some other witnesses and say, can you tell me is this conditionally independent or not? So I can look at the empirical distribution and look at how far from independence is it. Right? For instance, I use mutual information to test that. And so this way I can kind of go about testing. Right? So let's say I fix node I can search over all sets of size D. So this is this. Size D, right? So I can, or less than or equal to D, it doesn't matter. So I can do the search over all the sets, and for each set, so for each set S, I can just test, right? Look at different nodes in the graph that don't belong to S and see if this property holds. Of course, if there's a violation, you say these are not neighbors. Is this clear? So it's more like brute force testing. I'm just kind of seeing if this property holds for all the nodes. Is there some violation? I could also do the other form, right, where I had the pairwise property. So if you recall the pairwise property, I had like two nodes I and j be conditionally independent if they were not neighbors, right, if I conditioned on the rest of the graph. So I can also use this property to test, because here I could say, if I have I and j, right, I don't need to condition on the rest of the graph. All I need to do is to condition on some small size set, right? The size depends on the degree again, because if they're not neighbors, I can always find like set of nodes, right, that are connecting the two, and this set will be of size less than d, which is the degree. So I don't have to condition on all the nodes in the graph. I can just condition on size set d, right? So I can search over all the different sets and see if it becomes conditionally independent or not. Right, but all this involves, it's exponential in D, right, because I have to look at all sets of size, D. Is this clear? So if the degree is small, I can do this. If the degree is large, I can't do this. Is this clear? Right, I'm essentially brute force testing the property. Right, and I have my empirical distribution. I can check based on my empirical distribution if there is conditional independence or not. Any questions here? Is this clear? So in certain cases, it turns out it's more efficient than this. If you have the property of being like locally tree-like, right? These are kind of like some, or locally it's kind of like small number of nodes, and all the loops, right, are kind of much longer, right? So those are called locally tree-like graphs. Then you can kind of argue if there is correlation decay. You don't have to search over the degree of the nodes, which could be large, right? You could do better than that. In fact, you could just have like size 1 separator or size 2 separators. So there's some, again, additional properties you could argue in terms of when there is correlation decay to make it more efficient than this brute force search. But then that takes in kind of also look at how do the correlations decay, and can I approximate my separator set here to be smaller than what's absolutely required in the general case. But that's a detail, right? So that's, in some cases you can get more efficiency, but for the general case, you would have to search over sets that are exponentially growing in the degree. So yeah, between trees and general graphs, right, that's why there is a big gap. Right, trees, you just kind of had this nice property, and we also know how to compute minimum spanning tree efficiently in trees. But for general graphs, I can just kind of do this local testing property, right? It's not something global. Whereas here, I was globally maximizing, which was nice. There, I'm not globally maximizing anything, right? So this does not guarantee its maximum likelihood estimation, right? So these kind of things, what we're doing, it does not guarantee any statistical efficiency, right? It's consistent. I mean, if you had an infinite number of samples and you had this exponential computation in D, you can find the correct one, but it's not maximum likelihood. Whereas for tree, we got the maximum likelihood. Okay, great. See you next week.